Going to plunge in and look at a number of Lie groups and Lie algebras and work with them explicitly and then come back to a more abstract approach. Certainly the first of these that we will investigate is the most important to the physicist, and this is called the Heisenberg Lie algebra. It is composed of position, momentum, and one other operator which commutes with both position and momentum. For those of you who have had quantum theory, this is basically quantum mechanics in one dimension. And one will first say, aren't we just doing quantum mechanics here? The answer is both yes and no. The mathematics stands by itself independent of the quantum mechanical interpretation. The quantum mechanics, or the physics, is the interpretation of the mathematics and its application to various problems. We will be talking about Lie algebras, which we will represent as LA, and Lie groups, LG, but primarily we will be emphasizing the Lie algebra part. Obviously, any of these Lie algebras will generate an associated Lie group. As we will be concentrating on the commutation rules and the structure constants and the mutually commuting variables in the Cartan subalgebra, it is natural that we concentrate first on the algebra itself and then on the group which it generates. Quantum mechanical observables for position, x, and its conjugate momentum, p, obey commutation rules xp is I, where I is the square root of -1, times an object capital I, such that capital I commutes with x and capital I commutes with p. This is a Lie algebra of order 3 that is nilpotent, it's not semisimple, and it is not in the sequence of all the semisimple Lie algebras that we first looked at a couple of pages ago when we did our overview of Lie algebras. It is one that's outside of that structure and that study. In particular, this Lie algebra, the Heisenberg Lie algebra as we're calling it, is such that the metric Gij would have a vanishing determinant. It therefore has an invariant subgroup, and we can see that in terms of the I itself. The I almost behaves like a Casimir operator. Even though it's not, it behaves that way, since obviously I commutes with any combination, linear combination of both x and p. The physical world of quantum theory has determined that I only has one eigenvalue, and that eigenvalue we write as Planck's constant divided by 2 pi, or h bar. H bar in the metric system is of the order of about 10 to the minus 34. It is an extremely small number, and one could say that to a good approximation, a world in which h bar was equal to 0 is a good approximation to much of our ordinary everyday life. And that's why we do not see quantum effects as we drive cars and ride bicycles. Certainly the car and other people do not have the wave phenomena and the uncertainty that we associate in the measurement process of quantum mechanics. And it's only manifested when we get into units of action, which are products of x and p. You recall that x times p is a unit of action, and therefore h bar is a unit of action in terms of its units. Only when units of action are of the order of 10 to the minus 32, 33, 34 that we begin to see the quantum effects, although there are exceptions to that naturally. But mathematically, there are separate irreducible representations for every real eigenvalue of I. So I actually has the entire spectrum from minus infinity to plus infinity of real eigenvalues that are acceptable. But once you're in one of those particular eigenvalues, there's no way to perform any transformation, nor do any operators take you to another one of those representations. Therefore, that representation is called irreducible, and it sits all by itself as a representation with no operator taking you out of that representation into another one. Therefore, in a certain sense, all of the different eigenvalues associated with capital I correspond to representations that are sealed from one another. So we have a continuous infinity of different representations, and only one of those corresponds to reality as we know it, the one where capital I has the value Planck's constant divided by 2 pi. In a certain sense, I also plays the role of the only Casimir operator for this operator, because no function of x and p commutes with all of x and p, so there is no nonlinear function that commutes with all of x and p. Consequently, there is no meaningful nonlinear function. Obviously, x squared and x cubed commute with x, but that's a kind of a non-trivial part that just commutes with part of it. It certainly doesn't commute with both x and p. Consequently, I plays the role of a Casimir operator even though it is a member of the Cartan subalgebra. And we will list, therefore, its eigenvalues. We can choose either x or p for our Cartan subalgebra, and this will be extremely important in our understanding of quantum mechanics. The basis for our representation space can either then be taken as h bar and x diagonal, which we will use, the eigenvalue we'll use as y to signify an eigenvalue of x, and k as an eigenvalue of p, normally associated with a wave number. Now, we are every single one of the representations that we have will have this h bar in it, and we get tired of writing this down. I'll write it a few times just to indicate that this is supposed to be here, and we're supposed to have this eigenvalue listed because it's one of the complete commuting observables. But later on we'll ignore it and not write it and just take it as being understood. So we see that we have a duality in this Lie algebra. Whether we take I and x as being diagonal or I and p as being diagonal gives us two different representation spaces, and either of those representation spaces is a totally valid one. The critical thing, and I will come back and repeat this a large number of times, is we learn to visualize things from the time that we grow up in a space and a time that we use psychologically with our vision and our hearing and all of our senses to order the occurrences around us in the real world. Events occurring in this space-time structure are things, therefore, that we say that we understand. We don't understand these other spaces. We only understand x, y, z, and t, three-dimensional space and one-dimensional time. Therefore, to a great extent, even though we may use other spaces for other reasons, only when we can relate something back to a distribution or an eigenvalue or a parameter or a shape or a sound or something in our three-dimensional world do we say that we fully understand it. Although technically we say that we understand something when we can predict its behavior. Thus, on our Heisenberg Lie algebra, the Casimir operators, I put quotes around that because it's not really true, is I, and the Cartan subalgebra is either x or p. Therefore, the representation space is either h bar and y being an eigenstate of x, or h bar and k being an eigenstate of p. We write, therefore, x times y is y times y, where x is an operator and y is a number. We will notice that in using the Dirac notation, this is a ket vector out of the one that aims in the other direction. It's called a bra vector, that we label the interior of our ket vectors and our bra vectors with eigenvalues of operators that simultaneously commute. Therefore, here we're labeling the inside of this ket vector with the eigenvalue of the operator x. Likewise, we label the inside of the ket vector that is an eigenvector of the operator p with the eigenvalue k, and we can see that operator times representation space is equal to a value times that vector back again. By this equation, we are therefore saying that this is an eigenvector of this operator with eigenvector k. We're now going to leave this h bar as being understood in all of the vectors in the representation space that we deal with. Now, one of the first computations that we want to study is if we take e to the minus I over h bar times some parameter epsilon, and this is an epsilon right here, it's not totally clear, times p, an infinitesimal transformation generated by the operator p. What does that give us? Well, we're going to take this infinitesimal group element, act upon this eigenstate of position, and then see what eigenvalue does this have? Does this whole object have? Well, we can expand our exponential and write it in the following form. This is 1 minus I epsilon p over h bar, and the rest of the terms in that infinite series expansion, of course, are epsilon squared in higher order, which can be neglected. We can then break that out as x times 1 times y, which is y times y, because that's an eigen vector of y, minus I epsilon h bar x times p. Of course, these are just numbers, so the operator x moves smoothly through those numbers until it gets to the operator p, and these do not commute. Rewriting that again, we see that we have y times y from the first term, minus I over epsilon h bar, times, and I'm now going to write the xp from the commutator that we have, which is xp is equal to px plus ih bar, and that comes from the commutation rules. Writing that down and then expanding the terms, we get the following. First of all, as this x hits this y, we get another y, which we have brought outside, factoring it with this equation right here. So when this x hits this y, we get a y. We take these two terms, bring the y out front, and write it as y minus I epsilon over h bar times p, times the vector over here. I probably should write that for completeness, have that vector here again. The second part is I times a minus I gives us 1, h bar divided by h bar gives us 1, and we're left with epsilon times y itself. But epsilon times y is equal to epsilon times 1 minus epsilon over h bar p. Why is that? Because epsilon squared is of higher order and can be neglected, times y. And therefore, we can write both of these terms here and over here as e to the minus I epsilon p over h bar times y again. This is what we have on the left-hand side. On the right-hand side, we now get, from this term up here, y plus epsilon. And what have we done there? Well, we've taken, in order to make this term something that we can factor the epsilon out of, just as we factored the y out of this term, we added another whole term here that's identical to this right here. And we can do that because that would be a term of order epsilon squared, as we have shown here. Therefore, we get y plus epsilon times that whole term occurring in both places, which can then be written in the exponential form. Thus, we reach the conclusion that x times this exponential with an infinitesimal represented here is equal to y plus epsilon times that same state of back again. That means that this vector right here, which is this operator times this vector, is an eigenstate of x with an eigenvalue y plus epsilon. Therefore, we can write this state in the following form. We can write this as being y plus epsilon. Now, obviously, if we can move forward by an amount epsilon with the operator p, p then becomes a translation operator that moves us forward with this group, and p generates this group transformation. and moves us forward from a position y to a position y plus epsilon. Now we can continue this process, and when we do, it follows that y has a vector for every real number from minus infinity to plus infinity, and e to the I over h bar alpha times p translates the system from the state y to the state y plus alpha. Consequently, starting with any one state of the system, which is a position eigenstate, it follows that this group of translations generated by the Lie algebra consisting of the operators alpha, a real number, times p, will translate the system to any other position that's possible on that real line. This is an incredibly important result, and we notice also that this operator, in doing that from the point of view physically, also mathematically is raising and lowering the eigenvalues by any given amount. So by putting in a plus alpha, like a plus 7, we can raise the eigenvalue of y to y plus 7, or we can lower it to any other amount. Therefore, at the same time, this becomes a raising and lowering operator for infinitesimal transformations of the system. Because of the symmetry of the system, it follows that x will do to the p space what p does to the x space. X will actually change the momenta from p from one value to another, and p likewise has a complete continuum of values from plus infinity to minus infinity, because the Lie algebra of xp and I1 is symmetrical between the two operators. Thus, both x and p have eigenvectors and eigenvalues that span the positive and negative reals. As these eigenvalues of Hermitian operators are orthogonal, we can choose a normalization for the vectors. We already know that they're orthogonal. We can choose a normalization so that y1 times y2 is the delta function of y1 minus y2, where this is the Dirac delta function. Likewise, k1, k2 is normalized to give us the delta function, delta of k1 minus k2. These functions are such that you will recall that their integral gives us a total value of 1. We need the transformation now to take us from a vector y to a vector k. We have already found the transformation that takes us in from any one y to another y and any k to another k. We now want to be able to move back and forth between the position and momentum representations. In a certain sense, one can think of it in the following way, that one observer says, I want y to be diagonal. Another observer says, I want k to be diagonal. One takes the position representation, one the momentum representation. This is exactly analogous to two people looking at three-dimensional space, and one saying, I choose this I, j, and k as my orthonormal basis set for the space, and another one says, I choose this set over here. The transformation back and forth between these two sets of three-dimensional unit vectors, orthonormal unit vectors, is determined by the projection of each vector onto each other vector in the other system, which is, since these are unit vectors, becomes the cosine of the angle between those two vectors. Between three vectors and three vectors in one system and three vectors in the other system, we therefore have a total of 9 possible projections. These 9 projections are all the cosines of the associating transformation of the angles between them. So, for example, you have the cosine between the I vector in the first system to the I, the j, and the k vectors in the new system. And to have those 3 directional cosines for that, and then for the j, and then for the k, allow one to know exactly how one observer is seen relative to another observer's coordinate system. That's exactly what we're doing here with 2 infinite dimensional basis systems, that of x and that of p. Now, in order to do this, we'll use some tricks that will reoccur again and again in all of our work with Lie algebras. And this technique, therefore, is important not only for our derivation here, but for the general understanding of how the raising operators are used in order to look at the spectrum and generate the various eigenvalues and the transformations between them. Now we recall that e to the I epsilon p over h bar y is expanding that exponential to the first order, this term right here, and that is also y plus epsilon. Now we're going to multiply that out and we get this form right here. Or we can say, by solving for p, that p is equal to, here we see the first term minus the second term divided by epsilon and multiplied by h bar and I. And that is the solution of this equation right here for the operator p acting on y. So p times y is equal to IH bar times the change, the infinitesimal change in the state divided by epsilon. Well, that's nothing but the derivative with respect to y of this vector. So consequently, we can say, and this is a very important result, that p times the ket vector y is IH bar d by dy of y. So p performs the differentiation. It is because of that this algebra is so incredibly important, because it gives us not only the connection to our regular space and time in terms of position, these other momentum operators give us differential actions upon that space that not only translate us or move us infinitesimally forward and therefore can move us finitely from one position to another in the translation, it also gives us the ability to do action by differential linear operators. Therefore, various functions of these p's become functions of differential operators, differentiations. So we can, if we take p squared, we would have a second derivative. So we can see back now that the Heisenberg algebra does far more than it appears simply on the surface. It gives us a connection between differential equations on functionals and the associated Lie algebra. Now, because we can write this equation, we can take now the Hermitian conjugate of that, and since p is a Hermitian operator, when this acts backward on y, we found that this gives us minus IH bar d by dy on the bra y vector. Remember, this is the ket vector, and this is the bra vector, and that's because the pair of them together form a bra-ket, or bracket, as Dirac originally envisioned it. By symmetry from this, remember the only difference in x and y is a sign, and so by symmetry we can immediately jump to the conclusion that x times k will give us I times a minus I h bar d by dk of k, and the Hermitian conjugate relation is given by this. These results right here, lay the foundations for essentially all of the differential equations in quantum theory. All of those differential equations issue from these representations of p on the x diagonal representation y, and the position on the momentum representation k.